I can't tell you how dismayed I am at myself for the errors that were in the midterm, and for that matter on assignment 7. But anyway, thanks to Bryson, 3 more problems were identified on the midterm, and we fixed them. So number 29 had a typo, and so I've just lowered the credit to 0 on that one. Questions 44 and 45 were true false questions, and the correct answer that was put into the system was wrong. It was, I forget, it was should have been false and it was true, or vice versa. Anyway, that was fixed. You can find all of the, I mean, on the exam site, you can find what it was. But in any case, those modifications are made and the system automatically regrades. On the average, this will improve the scores of some of the average student. In assignment 7, the last objective, which
Is the third one look like?
mm-hmm. which was this one here, was modified yesterday. It was wrongly stated. I've made it correct, but I've now said it will be extra credit, right? In other words, if you do everything but not that, you'll get full credit for the assignment. And if you do that one as well, you'll get extra credit. I did that because assignment 8 is now up. And it's more important that you get to assignment 8 than that you do this last section of assignment 7. Okay, so if you have time to do both, fine. Yes?
So that's the rotations on the MATLAB grader?
No, it's the reverse rotations.
But
The idea was essentially to see what happens when you rotate forward and then rotate back and get a comparison. And it was the rotate back part that was this last section. But you still have to rotate forward. There seems to have been some people who have questions about the MATLAB grader. The person who wrote it is Alan Lee, and he apparently is going to be at his office hours today. So if you have questions about that, it'd be best to pose it to Alan. Any question about all that? Sorry for all this, I don't know, getting the details correct is a challenge. Just to let you know where we're going, we only have today's class and 3 more in the semester. Today we're going to finish up the geometric transformations material, I believe. Thursday there's no class. Next Tuesday we'll be talking about height ridges and their interpretation for finding edges and edge strength and bar strength. And maybe a little bit of that left over on that Thursday, but on Thursday's mostly dedicated to a course summary, right? Summary for the whole course. And that will continue on the following Tuesday. I will be taking questions about the material in the course, and if the questions run over class time, I'll schedule another time for a special session for those who want to ask further questions. Also, assignment 8 is due on the 23rd will have been graded by the 26th. And if there's anything I want to share with you about your performance on that, that'll take place there. And if you have questions about the grading or anything like that, you can bring those up as well. Any questions about that? Okay. Okay. We were talking about homogeneous coordinates last time, and one of the beauties of homogeneous coordinates is that they deal with perspective. And perspective is important for dealing with the relationship of images that you take with an ordinary camera relative to 3 space, where the scene exists, and likewise for X-rays, that is to say for radiographic imaging. And the idea is shown in the figure over here. You have a viewpoint that has a central direction, and you need to first rotate the whole space so that the viewpoint is along the pure z direction. That is to say, the data's out here, and the screen that you're thinking about projecting on is here. And of course, this is from 2D to 1, but actually this line should be thought of as coming out of the board, right? It's a plane, and you have your camera here. Okay, so the plane is orthogonal to the view direction. I'll put it another way, the view direction, the pure z direction, is the normal to the plane in the direction. Clear so far? Okay, so that requires a rotation from x, y, z into x prime, y prime, z prime, and we know how to do that with a homogeneous, a matrix of homogeneous coordinates, which has that rotation matrix in the upper left-hand 3 by 3, and a 1 in the lower right, and zeros elsewhere. Okay, once you have things set up like this, you're interested in where any point out here that's at depth z prime and distance in this direction x prime, or in 3D x prime y prime, where it projects onto the screen. Right? And so you're interested in what this leg is. And the point is that you got similar triangles. This triangle and this triangle are similar, which is to say that this is to that as this is to that. And assuming we know how far away our screen is from the camera, that's D. If you work it out, you'll see that the position here, this distance, x double prime, satisfies x double prime equals d x prime over z prime. That is to say, we need to be able to divide by z prime to get x prime. And the beauty of homogeneous coordinates is that you understand that x, y, z, w is the same thing as x over w, y over w, z over w1. So we have a setup where division by the fourth coordinate is assumed. And so if you have a 1 there in W, then XYZ1 just means XYZ itself. But if you have a W there, and in our case we're going to need something that involves Z prime down there in the W slot, then we'll be able to understand that it's divided by W. Tricky, huh? Nice idea. Okay, so what I have here applies to X prime, and also the same thing applies to Y prime, right? The Y coordinate is also going to need to be multiplied by D and divided by Z prime. So we have these, what I just said, we have these homogeneous coordinates, x, y, z, w, 4-tuple, which we understand as to be equivalent to just as I said. And what that ends up being is you want to multiply your x prime 1 vector times by a matrix P, 4 by 4 matrix, that's this guy. Okay, so you have x prime, y prime, z prime 1, and you're going to multiply it by P, the matrix. And when you do that, you will see that you end up with an x double prime, y double prime, z double prime, w double prime. That is dx prime over z, dy prime over z, dx prime over z prime, dy prime over z prime, z double prime, which is 0, and you don't care about it because we're not interested in the z value once we've projected, and d. But of course, that homogeneous thing is each one of these divided by d, which is to say x prime over z prime, y prime over z prime, 0, and 1. Right? So you've done the job you want. You multiply by this P matrix, and you've got the projected locations on your plane, on your view plane. Homogeneous coordinates allowed us to do that as a transformation, essentially from 3D to 2D projection on a plane. Questions? Another thing we would like to be able to do is if we have 3D data, like from for example, a CT image or an MR image, where you have an intensity at every place in 3 space, sometimes you want to be able to take a plane through that, some kind of a plane, anyway, cut through that thing, and you'd like to know the slice on that plane. You know, just cut out that slice. This is not projection. Point is that you're going to have pixels in that slice plane. And so the idea is rotate so that the slice rotate all the data so the slice is in XY. And then you'll have a particular z value that designates the plane. It's an XY plane at some z in the rotated z, right? And once you do that, you have pixels in z, and those will not be the pixels of the image at z, right? Because, well, for I guess obvious reasons, there's no reason for them to be. But they will be places in the XYZ image that you can do our standard interpolation method in, like trilinear interpolation. And that's how you do it. Okay, so we now have both projection from 3D to 2D, or slices from 3D to 2D. By the way, for those of you interested in etymology, the Greek word tomos means slice. So tomography is slice writing, tomography. The next thing we might want to do is we have a three space of intensities. And what we want to do is project those on some plane here in such a way that you're acting like you have an X-ray. Okay, so we have an X-ray tube here. And what we're going to do is we're going to run rays from the camera onto this plane, view plane, and accumulate all the intensities there. That is to say, add them all up, right? And put that sum over here. If we can make that accumulation work like an X-ray, then we will be able to simulate X-ray transmission. And that projection is what we need to indeed do what's called digitally reconstructed radiographs. They get called by the letters DRRs, which can be very useful for medical visualization, but also it has a part in computed tomography reconstruction, understanding those projections. In any case, what happens in X-ray is that you have some intensity of your X-ray, right? And you're going to send rays of intensity I0 along all these different rays, and they're going to end up at the pixels on this X-ray, this radiograph, this X-ray image. And this image is what we're going to talk about as having intensity I, 2D image. And what the story is that if you take a little section here, it is understood to have a multiplicative attenuation factor. That is to say, if you have a value mu at this x, and the input is I0, the output from that little thing is I0 times e to the minus mu delta x, where delta x is the little short length between these positions. Okay, so what I'm saying is that at the input to that little interval, you have I0, and then the output is I0 times e to the minus mu delta x. Clear? Well, okay, so now that is the input to the next pixel, which is going to be I0 e to the minus, okay, so I'm going to write this mu of x, delta x. I0 e to the mu delta x is the input times e to the mu of x delta x. And now we have mu of x plus delta x. Times the same delta x. And what that ends up being is I0 times the product of the two e to the minus mu's. And so when the whole thing is done all the way through, what you have is you had I0 input. And the output here, which is I0 times the product, I equals 1 to n, where n is the number of little slots, e to the minus mu sub I delta x. Right? You just multiply by the attenuation factor mu and the length delta x. The mu's are called attenuation, which is the same, of course, as I0 e to the minus the sum minus delta x times the sum of the mu i's. Right? Because that's how exponential works. And so if I take the log of both sides, so this guy is I, that is to say this is I. And so if I take log of I, I'm going to get log of I0 minus delta x times the sum. I equals 1 to n mu sub I. Where the mu sub i's are the values of attenuation in your image space for all these positions that you go along. And so we can subtract out the log I0, or equivalently take log of I minus I0, and we do minus that, and we take 1 over delta x, and we get simply the sum. And so that was what I wanted to turn the problem into. It's multiplicative in fact, but the logarithm allows you to turn it into a sum. And so in terms of the attenuation factors, if you look at minus 1 over delta x log I over I0, you will simply get the sum of the mu i's. Right? So that projection then can be used to compute the actual simulated value of I from this formula. Thus, you're able to simulate radiographic projection, or any projection which involves summing along your rays, summing some 3D intensity values in 3D, along all the various rays. Clear? Okay, so we can use these projections, these transformations, and they are also the transformations that you get from CT. Because in CT, this is exactly what you do. You take, this particular form of CT is called cone beam CT. But anyway, you have an I0. The physics of the process produces this effect. You get an image over there, and then the deal is that you rotate the projection direction. You get lots of different projections. And then a bit of image processing turns all the collection of 2D projections back into a 3D image. And in fact, you have all of what you need now to understand that. I'm not going to go through it in detail, but I will just point out that it turns out that if you take all these images and back project them each back along these lines and put them in every place along the line and do that for each one of the projections, you get what's called a 3D back projection image. And if you apply one of our shift invariant linear operators to that is to say you filter it with the right filter, you get the CT image. Okay. Any questions so far? So I finished the section on projections, and we're going to go on now to deformations. And the first kind of deformation that we want to compute is, okay, so deformations mean that you have displacements, just like you saw in assignment 7, you have at any given point, at some point in the image, you have its position x, and you have a delta x, and x displaces itself to the position x plus delta x. Okay? That's what a deformation is. You get, as long as this mapping from x of given these displacement vectors, delta x, is 1-to-1, as long as that mapping is 1-to-1, that is to say, it is not the case that some other x also maps onto the same place. Don't want to have that. As long as this is 1-to-1, then you have an invertible transformation, and you can, and that is what we mean by a deformation. An invertible transformation, so that at every x we know where it goes to, or from every place y we know where it came from. Okay? Well, a problem that frequently arises. Okay, so this says, well, there are lots of situations where the transformation we want to do is deformation. And we give a list of questions there. I mean, go long at one time, should go long at a same lung at a different time has to do with the deformation of the space of the lungs. Hearts beat out in the real world, non-medical problems. Trees blow, they deform. If you looked at me when I was married, I weighed 140 something. I don't anymore. And so we all change shape a little bit from morning to night and a lot over the years. Unfortunately, our brains deform in a way of atrophy as we age. But the growth period. Anyway, the point is we want to be able to deal with these relationships between where something was at one time and where something was at another time. But another thing we might want to do and is to start with what's called an atlas. Okay, so at the National Library of Medicine, there is a female atlas called Eve and a male atlas called Adam. And what it is this particular person divided into unbelievably small voxels, and for every voxel you know in what anatomic place it is. Right? So this one's in the liver, this one's in such a blood vessel at such a part of it. this one's in the lung, and so on, right? Every voxel is labeled as to what anatomic place it is. And so a good way to segment an image of me is to deform me into Adam, or better still, deform Adam into me, and carry the labels. So if this voxel is in Adam's liver and it maps into a place in me under this deformation, then presumably that's in my liver. Right? So the whole idea is to get this deformational transformation from the atlas to me, and that ends up being done via image registration techniques, 3D image registration techniques that we're talking a little bit about here, but which are gone into in great detail in Comp and BMME 775, which is being offered in the fall, indeed by me next fall. In any case, we then want to be able to deform the atlas individual to a specific individual, and then we're concerned about how we do that. So all these things require deformations, either within an individual or between individuals. Okay, so we have this idea that if we map x to x prime of x, what we're doing is saying x prime equals x plus the displacement of delta x at x. So this guy's the displacement. And you've seen that already in assignment 7. Okay, so what you need then is to be able to have this displacement at every x, at every voxel. And typically, I mean, that's a hell of a lot of numbers, right? If you have 1,000 by 1,000 by, let's say, 1,000 by 1,000 by 500 image, that is to say, you have 2 to the, 29th voxels, each of which you need a delta x from. And that's way too much to store. And so one possibility is to do what you've done on assignment 7, that is to say, to compute the delta, to have the delta x's, the displacements, at a limited number of places in a grid, and then interpolate all the other ones, approximated by, for example, Kepler-Clark or Splines. But another problem that frequently occurs is that we're able to identify common places in the image. So, for example, we have the place where the trachea bifurcates into 2 bronchi. And we can find those places in our specific images, in one image and in the other image that we're trying to deform between. So we have these sort of landmarks that we can find in the respective images. And so what we're given is a collection of landmarks, x of I, and their associated x prime of I. For a bunch of landmarks, I equals 1. Right, so we know that this place moved to that place, and 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 so on. We have a bunch of displacement vectors, and so xi moves to xi prime, which is xi plus delta xi of xi. These are all right? So we're given pairs of where the landmarks went. And what we want to do is to interpolate x prime of x. Right? We want to find what, at any given voxel, what its displacement should be. And here the assumption is we truly want to interpolate. That is to say, we want a function that x prime of x, we want a function x prime of x which literally has the property that at each one of the xi's, it has the value given in the data, namely xi prime. Right? So we want an interpolative, smooth mapping between xi and the xi's and the x primes at the xi's, and that gives us a value at any x. And okay, so this is what I've already said, except for this last item, which I will talk about now and then come back to the particular method of doing this interpolation. One way to think of this is that an xi is at some time I'll call t equals 0. And xi prime is x at t equals 0 and x equals xi. And xi prime is x at t equals 1 . And what we're trying to do is to find some path from xi to xi prime that we can think of divided into little time intervals. So it's here at t equals 0, it's here at t equals 1, at t equals a half, it's halfway along this curve. At t equals 0.75 is 3/4 of the way along this curve. And so from that point of view, we're trying to understand these little velocities at each time. And so if we multiply it's the velocity times delta t, we'll get this vector and this, then this vector, and then this vector, and then this vector, and then this vector. And when we integrate a so-called line integral along that, we will get the overall transformation from xi to xi prime. So what we want then is not simply n values, but n times m, where m is the number of velocity samples between time 0 and time 1. Notice this isn't real time. This is interpolation time. This is not the time, for example, that the heart is breathing or something, is beating or something like that. This is this fake mathematical time. Okay, so then instead of solving the problem of what all the delta x's are, we need to solve the problem of what all the v's are. And if there are mv's, if you thought you had a lot of delta x's to compute, we have m times as many things to compute. And it turns out that doing the registration on the velocities has some very significant advantages. And among them are a guarantee of this 1-1 behavior. And there's a whole set of methods that go under the acronym LDDMM, Large Deformation Diffeomorphic Metric Mapping. Never mind, you don't have to memorize that. The point is that these LDDMM methods are of this velocity version stuff, and they have some wonderful methods on websites that you can make use of if you want to make deformations based on image to image intensity. So you're trying to deform the input image to the output image so that the deformed input image is as close as you can make it to the output image. Right? But we're not going to solve that problem here because it's way beyond the capability of, the material in this course, the scope of this course, but it is covered in 775. And we are going to talk about this problem where the input is not two images, but two sets of corresponding landmarks. X1 and X1 prime is X2 and X2 prime, X3 and X3 prime, right? A bunch of landmarks that are in no particular place, not in a grid. They're not required to be in a grid. Any set of xi prime, xi double prime will do, will work, okay? And so the method we're going to be talking about was invented by a scientist named Frederick Bookstein. And Fred was a wonderful scientist, but an awful writer. And so you shouldn't try to read his papers. But rather, there's a wonderful book. I think I have a reference to it here. Dryden and Marty's Statistical Shape Analysis. And these guys write really well. And so if you want to know about thin plate splines method, don't look up under Bookstein, but rather Dryden and Marty. Anyhow, I'm going to tell you about the thin plate splines method. Well, the first thing about it is that it's a misnomer. Essentially, from your point of view, it's a misnomer. It's neither about thin plates nor about splines. Okay, I'm sorry for the confusion. It has to do with a particular physical model that behaves mathematically in a similar way, and I'm not going to get into that. Take it as TPS. Don't get confused by the name thin plate or by the name spline. Okay. The basic idea is that you have infinite number of smooth transformations between the xi's and the corresponding xi primes. And for any given one of those deformations, you can come up with a energy according to some physical notion of energy that particular so-called bending energy that particular transform entails, right? And the deal is to find that particular deformation that of all those transformations has the minimum energy. You want the least work that produces a smooth transformation. And I didn't say one-to-one. I started to, and I should, because thin plate splines does not guarantee one-to-oneness. Okay, so we want a minimum energy transformation according to a particular measure of energy. And the beauty of this particular method is that when you write down that problem, that minimum turns out to involve solving a set of linear equations. Okay, and we know, that's a pretty quick thing to be able to do. Okay, and so computationally, it's beautiful. Whether the transformation it produces is beautiful, well, it does in many cases, and it doesn't in many cases. You'll see why. Okay. So, we don't want non-one-to-one transformations. We don't want truly irregular ones. That's we want them to be smooth. So here is an example of a pair of images with a set of landmarks, the end of the eyebrows, the ends of the mouth, the sides of the nostrils, and various eyes. And we want to be able to find a deformation that goes from here to here. Here's an example that appeared in the early work of Bookstein. Okay, so we need a deformation, but typically you do much better by sneaking up on the deformation and first figuring out what transformation is best purely in terms of a similarity transformation. Okay, and the similarity transformation that we want on landmarks is called the Procrustes transformation. Procrustes was in Greek literature, and it was a guy that was put on a bed, and he had to fit that bed, and so they deformed him to fit the bed. So that's where the name comes from. But in any case, the basic idea is you have this set of landmarks, the pairs, and the first thing you can do is to take the average of all the landmarks in the source and equivalently the average of all the landmarks in the target. And what we want to do is a translation. Translate this average onto that average. Okay, so now we have a new set of exabytes that are the translated versions of the original exabytes, but now they agree in center of mass, in average, with the X prime sub i's. And then, so now you have, I'll call these the X sub I translated. And what I'm going to want to do is to take the distance to the origin, which is now where so what I really want to do is to translate this guy to the origin, 0, and this guy to the origin, 0. Okay, so if I've translated to the origin, the distance from the origin is now just the vector from the origin. Distance is the magnitude of the vector. And you can take the average square distance to the origin, root mean square, and divide the translated version by that average distance. That just scales everything so that the average distance to the origin is 1. Okay, so that's the scaling. And you can do that for for the primes as well. And so now you have scaled source landmarks with a common center with scaled target landmarks. And the final thing you can do is to rotate this new set of landmarks into the other set of landmarks in such a way as to minimize the sum of the squares of the distances after the rotation. So you know how to do a rotation. We'll figure out which rotation you need. It turns out to be the eigenvector. The rotation matrix turns out to be the eigenvectors of a particular, the so-called second moment matrix. And you will see in your assignment 8 that you're going to need to compute a second moment matrix. And the point is that if you have each xi as xi, yi, zi, its position in 3 space, and if I rename these as xi1, xi2, xi3, where the sub 1 just means it's x, and the sub 2 means it's y, and the sub 3 means it's z. Then if you take xij, xik, summed over I, and make a matrix whose elements, a 3 by 3 matrix, whose elements are c, j, k, you get a matrix C, and it turns out the eigenvectors of that give you the rotation that you want to normalize this thing to a standard orientation. And you can do that to the x primes as well. And so we will have rotated everything, translated, scaled, and rotated everything into a standard coordinate system. And it turns out to be useful to do that before you start thinking about thin plate splines or any other registration. So the idea is that you pre-process by the similarity transformation computed from Procrustes, and then you apply thin plate splines. The thin plate splines would have worked on the original data, but it isn't the same as it's doing that would not give you the same result of doing Procrustes and then thin plate splines. And it turns out the one you want is Procrustes followed by thin plate splines. Okay. So this Procrustes transformation between the x's and the x primes, it doesn't matter whether you do it, which are the x's and which are the x primes. If you want to rotate the x's into the x, or transform the x's into the x primes, since everything is provided for each one separately, except the rotation, the rotation you go from primes to non-primes will be the inverse of the one you go from non-primes to primes. Okay, fine. So we have this Procrustes transformation that we'll use as pre-processing. And now we will want an energy measure that we're going to minimize. And there are a bunch of energy measures that are around. But the one that we're going to use is something called the Frobenius norm by mathematicians. Okay, and why Frobenius norm? Well, because it's sensible and it yields a really nice solution. So what is this Frobenius know? So now we have all these, our data, but everything has now been Procrustes normalized. So these xi's are all Procrustes normalized, and so have the x primes. Consider that function, this continuous function, x prime of x. X prime has an x component, a y component, and a z component, each of which are scalar. So these are three scalar functions of three variables, right? The basic idea is that the energy is going to reside in second derivatives. So the idea now is that affine transformations are going to have no energy. It isn't going to have any cost to move things around by matrix multiplication and the addition of constant. So our overall transformation is going to be ax plus b plus some other function okay? And since all the linear stuff is supposed to be taken up into here, what's left is second order stuff, second derivative stuff, right? If you think of a sort of a Taylor series. And so this is going to be this f that we're going to be interested in is going to involve all the second derivatives of this function. Let's be careful. For every scalar function of three variables, how many second derivatives are there? We learned that at the beginning of the course. It's a two tensor. Right? You have the Hessian. d2 x prime by dx squared d2 x prime by dx by dy d2 x prime by dx by dz d2 x prime by dy by dx, which is the same as that guy, d2 x prime by dy squared, d2 x prime by dy by dz, and you're going to know what I'm going to put down here. It's d2 x prime by dz by dx, d2 x prime, can't read this anymore, by dz by dy, and d2 x prime by dz squared. Okay? Now, of course, there's symmetry in these guys. So this guy is that guy, and this guy is that guy, and so on. But you can think of it as being a 3x3 array of derivatives at any given particular location x. And we need to have that set of derivatives for y prime as well, and for z prime as well. So we're going to get 9 times 3 second derivatives, 27 second derivatives. The Hessian for this guy, the Hessian for this guy, and the Hessian for this guy. And we're going to be interested in the size of those second derivatives. We don't care whether the function is going up and over or down and under. We're interested in how curved it is, if you will. And so we're going to take all 27 of those second derivatives and we're going to square them, just because we don't care. Okay, and so what we get at any given point, we get the sum of the 27 squared second derivatives. Okay, and that's at a point. And now we're going to integrate over all x. All x, all y, all z. The whole infinite space. So this is, strictly speaking, this sum is the Frobenius norm at a point, and this is the integrated Frobenius norm, integrated over all of space. And we're going to let that be our bending energy. You don't actually have to compute that. The program that you will use does all this math. But the upshot is that what it's trying to do is to minimize this particular norm of the function x prime of x. Trying to have that x prime of x that minimizes this integral Frobenius norm. And you do the math on this, and it turns out that what you end up is solving for a particular solution where this f of x is the sum of what's called radial basis functions, these u functions. So you want to know at a particular x what it is. You look at the distance of x from each of the landmarks in the source image. That's just the distance. And you use this magic function u, which is called a radial basis function. And what we're going to be doing is solving for the a's, the 9a entries, the 3b entries. And this thing has an x component, a y component, and a z component for each of the basis points. So there are 3n values. And we're solving 3n plus 12 linear equations in 3n plus 12 unknowns. Okay, and that set of linear equations comes out of the math that shows that the minimal, what those linear equation solutions do, indeed minimize this Frobenius norm. Okay, so when all is said and done, you're going to solve for these 12 variables. Once you have the function x prime of x. You can apply it at any x you want. Okay? The function u is a function on scalars, right? You put in distances. And it turns out that the u's that you need are, well, they come out from an impulse response function analysis. that I won't go into. But for 2D, it turns out that u of d is d squared log d. And for 3D, u of d is d cubed. Those are the scalar functions that you end up using, right? They are those u of d's for various values of d produce these so-called radial basis functions. Okay, so that's thin plate splines. It has a number of nice properties, but a few that the nice properties is it produces a very smooth mapping, right? Yeah, it's set up to minimize second derivatives, square second derivatives. That's going to be very smooth. However, it's not necessarily one-to-one, but it will be if the experience if the displacements that you're putting in are small relative to the spacing between the points. Okay, so in reasonable application, where you've done the pre-processing by Procrustes, and therefore typically you do have these small displacements as inputs, it will produce a one-to-one mapping. Or if it doesn't, there's an LDD-MM method that's much more complicated that you can use in its place that will produce a one-to-one mapping. Surprisingly, it's affine non-invariant. That is to say, if you take the set of points and you apply the same affine transformation on the x's and the x primes, and then do this whole thing all over again, you will not get a transformation that is the same as the original transformation, but for, in other words, if you take the transformation and then you do the inverse of the affine transformation, you'll not get the same result, despite the fact that you would have thought it would. And it's not symmetric, meaning if you swap the primes and the x's, you'll get a transformation that is not the inverse of the transformation you get for the x, going from the x's to the x primes. But computationally speaking, it's a very, very nice solution. So I'm done with in-place splines. I guess I'll tell you where the name came from. It turns out that if you take a thin metal plate, infinitely thin, with constant mechanical properties, and bend it out of the plane, and now it's an infinite plate, you bend it out of the plane, and ask what the energy of that is. It turns out the Frobenius norm is what you get, and that's what the thin plate came from. But be careful, because this is not bending out of the plane. It's three different bendings, each of which is involved. Each of which, if you will, is behaving like a thin plate energy. Forget the thin plate. It's not patchwise, so it's not a spline. But it gets the name TPS because Fred Bookstein called it. Last slide in this lecture and on this whole series of geometric transformations. I have been talking about many of these transformations for continuous situations. But, of course, in the real world, we're going to apply that to discrete images with discrete voxels. you have seen that in your assignment 7, that the output image, the result of the transformed image, wants to be at a regular grid of pixels in I prime. And so you have to figure out what's the inverse transformation from I prime back to I. That's this G inverse. And that gives you places in I that you can then transfer into the pixels in I prime that you're after, or the voxels in I prime that you're after. Realize that if it turns out that the transformation you want can be understood as the product of two matrices, as it typically can, or more than two, the inverse of G1 followed by G2 is G2 inverse followed by G1 inverse. That's going to work for whichever G's you want to do for of all the ones we've been talking about. We've talked about rotations, translations, deformations, various other transformations, including the ones that don't go from 3 space to 3 space, but 3 space to 2 space, like the projection ones and the slice ones. Done with this section. Questions? Your final assignment, assignment 8, will have you doing a bunch of stuff with quaternions. What I want you to be able to do is to deal comfortably with quaternions. I'm also going to be sending you a set of exam type problems about quaternions. I'll end up giving you solutions to those, but you'll want to be trying those also, so that when I talk about them in this last summary lecture, you will have tried them yourself. Okay? But in particular, assignment 8 is going to require you to actually do some things with quaternions, to actually do some translations, to actually do some, do some rotations via quaternions, and to represent axes as quaternions, and so on and so forth. All right, and so this will give you some experience on that. I'm done for today.